delta H reaction from standard enthalpies of formation. So how can we find out what delta H is? Well, we can measure it experimentally using calorimetry, bomb calorimeter, or coffee cup calorimeter, or we can infer it, we can calculate it using Hess's law. So we can use different chemical reactions, right, that we can add together like we were just doing. But we could also calculate that using what are known as standard enthalpies of formation or standard heats of formation. So delta H is the change in enthalpy. We can define zero, whatever's convenient. Why is 0 feet elevation at sea level? Because we agreed to call it that, right? Why? Because it's convenient, right? There's sea level all over the globe. Turns out it's not maybe as exact as we thought, but still, it works, right? So here, with energy, I mean, where is 0 energy, and how far away is something from 0? It doesn't matter if we're only looking at changes. So we can just choose 0. So what we chose is we chose to have enthalpies of formation of pure elements in their standard states be 0. So an element as you would find it like at room temperature in its natural state in nature, we'll call that 0. That's the starting point. So looking at all the elements as building blocks starting from 0. So how is that defined? So the standard state for a gas is the pure gas at 1 atmosphere. So that's like normal, right? For a liquid or a solid, it's the pure substance in its most stable form at 1 atmosphere and the temperature of interest, usually room temperature, 25. If we're talking about a solution, some substance dissolved, it's going to be a solution with a concentration of 1 molar. So there's like 1 atmosphere, 1 molar, like room temperature, everything kind of the same. So standard enthalpy change is delta H naught. It's got this little degree symbol here, and that represents standard. So the standard enthalpy change is the change in enthalpy when all the reactants and products are in their standard states. The standard enthalpy of formation, so we're just adding junk onto this delta H, aren't we? Now we have delta H with this degree and an F. F for formation. That's standard enthalpy of formation. And that is for a reaction that forms 1 mole of that pure compound from its constituent elements. It's also called a heat of formation. So the elements have to be in their standard states because that was what was 0, right? All the pure elements have a heat of formation of 0. And so we're measuring enthalpy changes relative to elements in their standard states, just like we measure altitude relative to sea level. Because we all agreed that that's what we're going to measure from. So this is a table showing some standard enthalpies or heats of formation. There's a more extensive table in one of the appendices in the back of the book. So we can see that Br2 liquid has a heat of formation of 0. That tells me that that is bromine's standard state. Well, bromine is one of the 7 diatomic elements, right? So that's why it's Br2. And it's blue on the periodic table up here, meaning it's a liquid at room temperature. And so that's why Br2 at liquid is the standard state. Here we have 2 different forms of carbon. There's graphite and there's diamond. There's other forms too, but they're not listed here. Which of these is the standard state for carbon? For graphite, is graphite, because that's what has delta H 0. This one is not, it's a little bit above. So you can look up all these things. So we need to be able to write a reaction for forming a compound. So if we're looking at methane, the heat of formation is negative 74.6 kilojoules per mole. So 74.6 kilojoules of energy are given off for every mole of methane that gets formed from its elements in their standard states. So what are the elements in here? Well, there's carbon. We have to specify which kind of carbon. And there's hydrogen. Okay, so let's go back here and look at hydrogen. Where'd you go? Here. There's H and there's H2. H2 is the standard state. It's a 0. One thing that's a little different about these chemical equations is you're always going to have one product and it's going to have a coefficient of 1, because that's the definition of heat of formation. It's making 1 mole of it. If you're not sure what the standard state is, find the one in the table that has delta H0, and that's in Appendix 2B. Sometimes we're going to end up with fractional coefficients on our reactants, because we always have to have this equation showing 1 mole. So we're going to write the formation reaction for carbon monoxide. So here's our carbon monoxide gas. That's what we're writing it for. And then we're going to look at what are the elements here. Now, this formation reaction does not necessarily represent how that compound can be made. This is just a kind of a hypothetical thing. So we're going to split all the elements apart. I know some of you wanted to do that with the ionic compounds and the polyatomic ions. This is your chance. So we're going to have carbon and oxygen separately. And then we have to identify what are the standard states. Well, for carbon, it's a solid graphite as opposed to diamond. What about oxygen? Oxygen is a diatomic molecule, or diatomic element, right? So it's going to be O2, and its standard state is going to be a gas. So we identified the standard states. Is this a balanced chemical reaction? No, it isn't. But when we balance this, we cannot put a coefficient on the product. That's what's kind of different. I can't remember if I'm supposed to, yeah, here we go. So the equation has to be balanced, but coefficient has to be 1. So to make 1 mole of this, we're going to need 1 mole of carbon and half a mole of O2. So the oxygen comes in pairs, like a pair of shoes, right? And if here you just need 1 of them, you need half the pair, right? And then we can look up the heat of formation for carbon monoxide in the table, and it's negative 110.5. Any questions? Write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of delta H for each equation. That's my little cheat sheet. Just want to make sure it was there. Okay, let's do the first one first. So this is a formation equation for sodium chloride. So our product is NaCl in the solid state. What are the 2 elements in that compound? Sodium and chlorine. Okay? So we're going to have sodium in some state, and we're going to have chlorine in some state. What's the standard state for chlorine? Yeah, we could look it up, but we can also kind of think about it. Cl2 gas, because it's a diatomic element and the periodic table tells us it's a gas at room temperature. What do you think the standard state for sodium is? A solid. And we can look at the periodic table. Na is in black. It's a metal. It's solid at room temperature. It is not diatomic. It doesn't have any subscripts or anything. We could also go in the table and look that up. How are we going to balance this? The sodiums are fine. We have too many chlorines over here. We just need half of that. Right? So this is 1/2. And then we look up the heat of formation, which is over here. So these are arranged by different elements. And so this is not the one I need. This is the one I need, I think, hopefully, yes. So over here, there's sodium chloride. So to make sodium chloride from its elements in their standard states, negative 411.2. Negative 411.2 kilojoules. Pardon me? That's a degree, meaning standard. Yeah. Any other questions about that one? B. We're going to start again by writing the product, the thing that we're trying to make here. So PB NO3 2 as a solid. And that's our product because that's just what they told us to do. What elements are in this compound? Lead, nitrogen, and oxygen. We're going to list them out separately. So lead, nitrogen, and oxygen. Well, what do we suppose the standard state for lead is? A solid with no subscript. It's a metal. So a lot of the stuff you can find on the periodic table. If you're not sure, you can go look in the table of delta H's. How about nitrogen? That's going to be N2. It's a diatomic element, and its state is a gas at room temperature. Right? And then oxygen is also going to be a gas. Diatomic element, right on the periodic table. We have to balance this without putting a coefficient on the product. There's one lead here and one lead there, so that's nice. How many nitrogens are in this guy? 2. Nice, there's 2 nitrogens over here. How many oxygens in here? 6. So I need to put a 3 here to get 6 oxygen atoms. And then this is where I need this one. Lead nitrate is down here. Now this is Appendix 2B, and so it's got more stuff in here. It's got delta G and delta S. We're not going to use those. We're just going to use this first column. So here it is, negative 451.9. Any questions? Yes?
So right now we're just writing the equation, right?
Right. Yeah. We are writing a chemical equation that describes that heat of formation. And the reason we want to do this is because we could take a bunch of these equations and add them together to get the chemical reaction we want. using Hess's law. Okay? Woohoo, right? Just can't wait. I think we'll stop there. We'll just stop there.